Hello everyone, we're Group 4 and we'll be presenting Google Borg. I'm Moses and I'll be presenting the first part of this presentation, followed by Daryl and William. So to start off, we have an overview of Borg. Borg is a cluster management system used internally by Google, and it runs thousands of jobs from different applications across clusters with tens of thousands of machines. It admits, schedules, starts, restarts, and monitors a full range of applications that Google runs, including GFS, Bigtable, and Megastore. So moving on to the main benefits of Borg, we have three. First is that it hides the details of resource management and failure handling. It provides high availability and reliability for applications and effectively runs workloads on thousands of machines so that developers can focus on development and not have to worry about managing all these different machines. And at the time, this wasn't a new idea, but nobody was doing it at the scale and with the reliability and completeness that Google had accomplished with Borg. So moving on to terminology, we have some terminology that you should be familiar with before moving on to the next slides. We have tasks, which are running programs or binaries. We have jobs, which are groups of tasks. We have cells, which are sets of machines managed as a unit by Borg. And then we have the Borg master and Borglets, which are part of the cell. And we have the Borg master, which is a logically centralized controller that communicates with Borglets. And these Borglets are agents that run on each machine in a cell. From the user perspective, the users of Borg are the Google developers and sysadmins that run applications and services. These users submit jobs to Borg, and each job will run on a Borg cell. Now we move on to the high-level architecture. And this is a more complex diagram than the one I showed previously, but it shows how the users, which can communicate with Borg through the command line or web browsers, can send their jobs to Borg, and we know that the Borg master communicates with the Borglets, and this is all done in a cell. The cell is where all the machines act as one unit and are managed by Borg. And we have some other components like the Paxos store and the link shards and the scheduler that we'll discuss later. Now we move on to the workload. So there are two main parts of this. The workload consists of long-running services, and these services should never go down. And they're services that provide for end-user products and internal infrastructure. You can think of Gmail or Google Docs. Most of these are considered prod jobs. Batch jobs are less sensitive to performance disruptions and can take from a few seconds to a few days, and these are considered to be non-prod jobs. So like I mentioned before, we have cells, and each cell belongs to a cluster. So the machines in a cell belong to a single cluster. And the median cell size consists of about 10,000 machines with varying dimensions, meaning different CPUs, RAM, processor types, etc. So a cluster hosts one large cell, but can also host smaller tests or special purpose cells. And Borg provides transparency by hiding these differences from the users because it handles resource allocation, assigning tasks to machines, installing dependencies, and monitoring and restarting tasks. Here's a simple diagram I made of what a cluster looks like, just so you can better understand how it works. And we have a data center, and within that data center we have the cluster, which we know is a group of machines that can work together. And hosted on this cluster, we have one big Borg cell, and then we have smaller tests and or special purpose cells. For jobs, jobs can have properties like the name of the job, the owner of the job, and the number of tasks within the job. These jobs can have constraints, which indicate that tasks should run on specific machines with specific attributes, like a specific a processor, or a specific OS version. And these constraints can be hard or soft. Hard meaning it's a requirement, or soft meaning that it's just a preference. And a job runs in one cell, and a jobs can be deferred until an earlier job is complete. Now we have tasks. As you mentioned before, tasks are these programs that run, and each of these tasks map to a set of Linux processes running in a container. Now, the paper they mentioned that they don't use VMs because of the cost of it, and because their hardware at the time, the hardware that they invested in, didn't support virtualization. Tasks can also have properties such as resource requirements and the index or position within a job. Tasks from the same job share the exact same properties, but this can be overridden. Borg programs are also statically linked and packaged as binaries and data files, which Borg handles the installation. So how do users interact with jobs and tasks? Well, as we showed before, this can be done through the command line, but it can also be done through other Borg jobs or the monitoring systems. Job configurations are written in a declarative configuration language called BCL, and this is used to write the configuration files for jobs. Users can change the properties of some or all tasks in a job by submitting a new configuration telling Borg to update tasks to the new specification. And these updates are executed in a rolling fashion, but users can limit the number of disruptions caused by an update. If an update will cause uh, too many disruptions, it'll just be skipped. Some task updates may require the task to be restarted, such as when a new binary needs to run, or move to a different machine in the case of changing requirements or constraints of a task. Tasks can be notified with the SIG term so they can clean up before preempting with the SIG kill. And a notification is usually sent about 80% of the time. State diagram for jobs and tasks. There's a pending, running, and dead state. A task can be submitted, be accepted or rejected. If it's accepted, it goes into the pending queue, and then it waits to be scheduled. And then once it's scheduled to run, it'll move to the running state, and it can be preempted by another process, which will evict it back to the pending. And then when it finishes, it moves to the dead state. If it fails, gets killed, or is lost, maybe it'll be sent back to the pending queue. As you can see here, it can be submitted back to the pending. And a task in a pending queue can also fail, be killed, or be lost, and move to the dead state. Moving on to allocs. Allocs are a reserved set of resources on a machine in which tasks can run. And these can be used to reserve resources for future tasks, reserve resources between stopping and starting a task, and to move tasks from different jobs onto the same machine. Multiple tasks in an alloc share its resources. If an alloc is moved to another machine, its tasks follow. Then we have the alloc set, which you can think of as a job. You know that a job is a group of tasks. Well, an alloc set is a group of allocs that reserve resources in multiple machines and can run multiple jobs in them. Now we move on to priority quota and admission control. This is important because if you have a workload that you can't accommodate, you need to decide what should run and what shouldn't. Jobs have a priority represented by a small integer value, and there's a priority band from highest to least priority, including monitoring, production, batch, and best effort. High priority tasks can obtain resources from lower priority tasks by preempting them. We have to be careful with this because it can cause a cascade. So a higher priority task can preempt a lower one, which preempts an even lower priority task, and so on. To prevent this, tasks in the production priority band cannot preempt each other. And priority is important for running tasks or tasks that are waiting to run. And we move on to quota, which is used to determine which jobs are actually admitted for scheduling. And it's expressed as a vector resource quantities at a given time and priority. For example, you can request 20 TIB of RAM at production priority from now until the end of July and so XX. Quota is checked on admission, not scheduling. Thus, jobs with insufficient quota will be rejected. And high priority quota costs more than low priority quota. In the paper, they mentioned that users tend to overbuy quota, so they can counteract this by overselling quota at a low priority. Borg also has a capability system that gives special privileges to some users, allowing admins to delete or modify any job in the cell. Now we move on to naming and monitoring, which is important so you can identify where a task is. If the service needs to know where a task is and maybe it relocates to a new machine, it should be easy to find that task. So BNS assigns a name to each task consisting of the cell name, job name, and task number. The hostname and port number is written to a chubby file along with the BNS name, which is used by the RPC system to find the task endpoint. The BNS also forms the basis for the DNS name. As you can see below, we have the DNS name, which is made up of the BNS name. So we have 50, which is the task number, the job name, which is JFU. We have the user, which is ubar, cell, cc, followed by .borg.google.com. And the Borg also writes job size and task health into Chubby for load balancing purposes. So each task comes with a built-in HTTP server that publishes health and performance information, and this is checked by Borg, and it restarts tasks that do not respond to its request, or if a request responds with an error. There's also a service called Sigma, which is a web-based UI service that allows users to examine the state of all their jobs. But you can also drill down into individual jobs or tasks. And logs are generated, and to avoid running out of disk space, they're rotated. But they're kept for a while after a task exit to help with debugging. And Borg also provides guidelines on how to modify a job to better fit a cell if a job is not running. Job submissions, task events, and task resource usage are recorded for usage-based charging, debugging, and capacity planning. And this is all stored on InfraStore, which is a read-only data store with an interactive SQL-like interface. Now we have BorgMaster, which consists of two processes, the main BorgMaster process and the scheduler. The main BorgMaster process handles client RPCs, manages state machines for objects in the system, communicates with Borglets, and offers a web UI. This BorgMaster process is replicated 5 times, and each replica keeps an in-memory copy of most of the state of the cell. The state is also recorded in a distributed Paxos-based store on the replica's local disks. A single master acts as both a Paxos leader and a state mutator, and a master is elected when a cell is brought up or if an elected master fails. When a replica recovers from an outage, it resyncs the state from the other Paxos replicas. Moving on to the checkpoint, this is the BorgMaster state at a point in time. We have a periodic snapshot and a change log kept in the Paxos store, which can be used to restore the BorgMaster state, build persistent log of events, and for simulations. And we have FOMaster, which is a simulator that uses these checkpoint files to replay actual interactions that can be used for testing and debugging. Moving on to scheduling, the following steps are used. We have a job being submitted, and the BorgMaster records the job in the Paxos store. The job's tasks are added to the pending queue, and the pending queue is scanned asynchronously by the scheduler, and then the tasks are assigned to machines if there are sufficient available resources. Now scanning proceeds from high to low priority and is modulated by a round-robin scheme with the priority within priority to ensure fairness and avoid head-of-line blocking. So the scanning algorithm consists of 2 parts: feasibility checking to find machines for tasks and scoring, which determines which of these feasible machines to run the task on. Feasibility checking finds a set of machines that meets the task constraints and have available resources, and scoring determines the goodness of each feasible machine, which takes user preferences into account, but then there are other criteria that it uses, like minimizing the number and priority of preempted tasks, picking a machine that has a copy of the task packages, which is important, as we'll see later, and spreading tasks across power and failure domains and mixing high and low priority tasks to allow the high priority tasks to expand in the case of a load spike. So the original scoring system used EPVM was generated as a single cost value and aimed to minimize the cost when placing a task. So when a task needed to run on a machine, it would go for the one that had the least cost value at the time. Now this was good for spreading the load across machines, which leaves room for spikes, but it increased fragmentation. So large tasks that needed a machine where resources were being used couldn't run because it didn't have enough resources. Now the opposite of this would be packing machines tightly, where the advantage would be some machines would be empty, so those large tasks can actually be placed easier. The disadvantage of this is that it punishes misestimations on resource requirements. So let's say you have a task that actually requires more resources than you thought. Now you don't have room to expand. So the current scoring model is actually a hybrid of the previous ones. It tries to reduce the amount of stranded resources, which are resources that can't be used because another one is fully allocated. So let's say a task needs a certain amount of this resource, and we know that the other resource is fully available, but it can't use that resource because the other resource that it needs is fully allocated. Now this method provides 3 to 5% packing efficiency, the best fit for their workloads, and it allows them to preempt lower priority tasks to fit new tasks if there are not enough available resources. Task startup latency is highly variable, but the median is around 25 seconds. 80% of this latency is due to package installation, which I mentioned earlier is important because Borg likes to schedule tasks to machines that already have the required packages installed. Borg can distribute packages to machines in parallel through tree-like and torrent-like protocols. Now we're covering the Borglet. So the local Borg agent is present on every machine in a cell, and it starts, stops, and restarts tasks in that machine. It manages local resources through the OS kernel settings, rolls over debug logs, and reports its state to the Borg master and other monitoring systems. The Borg master pulls the Borglets for information on state and to send requests, so it has full control over the communication. So this avoids the need for flow control and prevents a recovery storm. And a recovery storm is when maybe the Borg master fails. So when it comes back up, instead of the Borglets flooding it with requests, it has to pull the Borglets instead. Now an elected master prepares messages to send to Borglets and updates the cell state based on their responses. Borgmaster replicas run a stateless link shard to handle communication for sub-Borglets. And Borglets report their full state, but the link shards aggregate and compress this information to reduce the update load on the elected master. If a Borglet doesn't respond to multiple pull messages, then it's marked as down and the tasks are rescheduled to other machines. But if communication is restored, then the Borgmaster tells the Borglet like, hey, these machines are scheduled somewhere else, so we'll kill the scheduled task here so there aren't any duplicates. Borglets can continue to run even if all Borgmaster replicas fail. So even if the Borgmasters fail, tasks can still run and services can stay up. And we move to scalability. A single Borgmaster can manage thousands of machines in a cell, and several cells have arrival rates of above 10,000 tasks per minute. The scheduler was split into a separate process so it could operate with the Borgmaster functions in parallel. The scheduler is also replicated and it works on a cache copy of the cell state, and the master will accept assigned tasks unless the assignments are considered inappropriate. And an inappropriate assignment is from a scheduler that was working on an outdated cell state. And separate threads were added to communicate with the Borglets and to respond to read-only RPCs, and these functions are partitioned between the replicas for improved performance. And several improvements were made in the scheduler to make it more scalable. We have score caching, which, as it sounds, caches the scores, and it caches until the properties of the machine or task change. We have equivalence classes, and they function by grouping tasks that have the same requirements and constraints and doing the scoring and feasibility on this class instead of doing it on each individual task. And then we have relaxed randomization, which instead of calculating feasibility and scoring for each machine in a cell, it picks in a random order until it's found enough feasible machines and selects a machine from the set. With these improvements, scheduling cell's entire workload took a few hundred seconds compared to 3+ days when these features were disabled. And I'll pass it on to the next presenter.
Hi everyone, I'm Daryl Korn and I'll present the following sections. One of the most notable aspects of Borg is its availability. Google claims the system reaches 99.99% availability, and this statistic is due to a multitude of reasons, more specifically the 7 that I have listed here. The first method they listed is that Borg systems automatically reschedule failed tasks. And the second is that developers tried to reduce correlated failures, and this is done by spreading job tasks over many machines or power domains so that one machine won't take down all the tasks for a particular job. Similar to method 2 is method 3 here, which limits the allowed rate of task disruptions. Essentially, Google ensures scheduled maintenance won't impact every task for a job. Method 4 mentions how Google desires their scripts to be able to submit forgotten requests. If a message gets lost, then it won't disrupt the system by resubmitting job tasks. Method 5 is rate limiting. So systems won't overly message unreachable machines and bog down the network. An unreachable machine could just be very busy. It hasn't necessarily crashed. Method 6 is to be efficient and avoid repeating tasks that lead to machine failures. The system tries to detect and prevent tasks that lead to these failures. And number 7 here is that after crashes, Borg attempts to recover important intermediate job data through logs. This way it can try to pick back up where it left off rather than restarting the entire job. On to discussing the performance metrics of Borg. First, we'll discuss how the authors evaluated the performance of Borg. First and foremost, the authors use a cell compaction metric to measure performance, not average utilization. Cell compaction essentially measures how many jobs they can fit onto a single machine. And this metric is fairer than average utilization because it accounts for fragmentation and works with heterogeneous machines, something that average utilization would ignore. Additionally, cell compaction directly translates to the cost and benefits of Borg because requiring less machines for jobs is cheaper and more efficient. Additionally, we should discuss some parameters for the following experiments. We should note that these metrics aren't from actual production workloads. They ran the experiments on simulations based on the production workloads. And the data for the simulation comes from a very particular moment in time. It was taken on a Wednesday, October 1st, 2014 at 2 p.m. Pacific Date Time. And this is essentially saying that the workloads represent a normal use day. It wasn't taken after hours. It wasn't taken on a weekend or a holiday. It's just people using Borg as normal. Some other parameters for the experiment include that small and testing cells were disregarded. Machines and their workloads were both heterogeneous, meaning that they varied in size and quality. And each experiment was run 11 times, which if you think that doesn't sound like a lot, then I'd agree with you. However, the authors mentioned that it was costly, even for Google, to run the experiments. So all the data, it's all the time and money they had to collect this data. Lastly, although cell compaction was used to measure performance, Google doesn't actually use it in their production workloads, and for a few good reasons. They want to leave a bit of wiggle room for workload growth and load spikes and other reasons. So while it's a good way to measure Borg, these metrics aren't entirely representative of how Google's production cells actually function. And figure 4 here shows just how much compaction the authors achieved for their experiments. And this is a cumulative distribution function, or CDF curve, which the authors use a lot in this paper. And it's a way to illustrate how the collection of machines responded to whatever is being tested here on the x-axis. And the x-axis here shows the size of the cells after compaction. So less than 10% of the cells greatly reduced in size, about 68%. On the other end of the spectrum, a few cells couldn't be compacted very much, and they remained at about 100% of their original size. However, most cells here in the middle, they compacted to around 70 to 85% of their original size. So let's get into the experiments, and the authors designed experiments to showcase 4 reasons that explained the efficiency of Borg. The first reason for Borg's efficiency is due to cell sharing. And this refers to how jobs are shared across cells. So machines will run production and non-production tasks in the same cell. So 98% of Borg cells are shared, which means that cell sharing is happening all over Borg, not just some of it. And since cells encompass multiple machines, as Moses mentioned earlier, if we go a bit deeper to the machine level, we find that 83% of the machines managed by Borg are running mixed workloads. And the authors estimate that cell sharing reduces the number of required machines by as much as 20 to 30%. And to further illustrate this point, we can look at figure 5a here. The dark blue bars show how much of the cells are used when we don't have cell sharing, whereas the light blue bars to the right are showing that we can fit many more jobs into the same amount of space. And figure 5b here tells a similar story. The x-axis shows how many more machines would be needed if prod and non-prod jobs ran in different cells. So about 10% of machines would incur just about 8% more overhead, while another 10% on the other end of the spectrum would incur as much as 50 to 60% more overhead, but most would incur about 10 to 50% more overhead. And we can see here that no cells became more efficient if we were to disregard cell sharing. So not only are cells shared across production and non-production jobs, but they're also shared across users. So similar to the previous 2 graphs, figure 6 here illustrates how much efficiency is gained through cell sharing. If we only have 5 cells, A, B, C, and D, and E, the yellow dots show what would happen if a new cell was created each time a user's workload consumed 10 terabytes of memory. And we can see the number of cells drastically grow because group A jumps from 1 cell up to 8, B jumps up to 10, and D jumps up to as much as 16. And the blue circles here show a similar phenomenon, but if the cell was split after 100 terabytes of memory was consumed. So the threshold is much higher, so there are less cells created, but it still increases overhead costs and uses additional machines. So the key takeaway here is that cell sharing keeps overhead costs and the number of machines down. Now, there are a few drawbacks to cell sharing. Cramming machines full of jobs will negatively impact CPU performance. So to test if this was true, the authors implemented some experiments and found the following 3 results. First, the authors found that adding more tasks to the machine didn't significantly reduce machine performance. Instead, they found that other factors played a much larger role, such as inherent differences in machine applications. Secondly, the authors found that CPU performance in shared cells was only about 3% worse when compared to dedicated cells. And thirdly, they found that jobs ran about 1.19 times faster in dedicated cells. So overall, the authors concluded that these drawbacks were pretty minor and didn't outweigh the benefits of decreasing the required number of machines. So the second reason for Borg's efficiency is due to the large cells that Google uses for its workloads. And this reason is pretty straightforward. Large cells allow large computations without dividing your resources, which leads to lower overhead costs. So figure 7a here shows how partitioning increases the overhead cost of Borg. We can see that with only two large subcells, the overhead cost from partitioning reaches about 50%, or it increases to about 50%. However, if we increase the number of subcells to 5 or 10, then this percentage increases to 150 or even like 230%. And figure 7b is telling a similar story. As the cell group increases the size of, or the number of subcells, then the overhead cost is also increasing for these processes. So if the same amount of work can be done with 2 cells as 10, then it's much more efficient to only use 2 cells. The third reason for Borg's efficiency is that users can request resources at a very fine level. So most cloud resources are requested through fixed size containers, but Borg users, they can request a very specific amount of these resources. They request compute through millicores, and memory and disk space are allocated at the byte level. And the authors estimate that this detailed level of resource allocation can reduce resources by as much as 30 to 50%. So figure 8 here is sort of illustrating this exact point, and it's showing that a majority of job requests, um, a majority of these job requests are falling into bucket, or would fall into many non-standardized buckets. Borg is getting requests for a really large range of these resources. So bucketing them would not be very efficient. And figure 9 sort of is building on figure 8, and it's showing the theoretical inefficiency if the devs did require resource bucketing. So the blue line is the lower bound of how much these resources would balloon, and the green line is showing the upper bound. And we can see that along the x-axis here, that overhead cost increases pretty dramatically with predefined buckets. So the last reason for Borg's efficiency is due to what the authors call resource reclamation. Users typically request more resources than their jobs require. And resource reclamation refers to how Borg takes these unused resources and distributes them to other jobs. The authors note that production tasks never run on reclaimed resources because you don't want to rely on that. However, it's estimated that about 20% of all of Borg's workload runs on reclaimed resources. So figure 10 here sort of poses a counterfactual question. What if Borg didn't reclaim resources? And we can see that the overhead cost dramatically increases. About 10% of cells would incur a minor 10% increase in overhead cost. Most would incur about a 10 to 40% increase in overhead cost, while a few would have a whopping 45% additional cost. So Borg would be much less efficient without this resource reclamation. And the final part of the performance evaluation covers how efficient and safe the resource reclamation is within Borg. So similar to figure 10, figure 11 is showing that users typically request more resources than they're going to use. The x-axis here is the ratio relative to the task's requested limit. So 50% means that the task only used half of what it asked, and 100% means that it used all the resources that it asked for. These dotted lines here, we can see that the CPU users sometimes go over the limit and they use more resources than they requested, but the memory, the blue dotted line, it hardly ever goes over 100% of what the users requested because Borg typically shuts those jobs down. And the y-axis is the percentage of tasks, so we can say that about 80% of Borg users here use about 60% of the CPU limit that they request, and they use about 80% of the memory that they request. These hard lines here, these are showing what Borg is reserving for the task. So that's why there's this vertical line here at 100%, because Borg is not going to reserve more than what it was requested for. Additionally, we can see that there's a pretty big gap here between what is used over here and what Borg is reserving down here. So this demonstrates that Borg's resource reclamation is pretty conservative and gives a very large buffer, so tasks are not going to lose too many resources. And since figure 11 here is kind of exposing just how conservative Borg is, um, the authors decided to test some more liberal thresholds for resource reclamation, and they changed the thresholds in live production cells, and they tested two different configurations, aggressive and medium. And medium's like a compromise between the baseline and the aggressive threshold. So we can see the results here in figure 12. The authors monitored for out-of-memory errors in this bottom section here. And out-of-memory errors are pretty serious because they're going to kill your task. Um, and we can see that these out-of-memory errors increase they increase a lot for the aggressive setting, but they don't increase so much more for this medium setting here. So the authors actually decided to change Borg's thresholds, and they eased the thresholds for resource reclamation to further improve its efficiency during this paper.
So far, we've seen how Borg schedules jobs and manages resources across a cluster. But once you start running many different users' workloads on the same physical machines, a new set of problems starts to show up. At a high level, the issue is that these workloads aren't isolated from each other by default. They're sharing the same CPU, memory, disk, and network resources. So, without some kind of control, one job could interfere with another. There are two specific types of isolation that Borg has to deal with. The first is security isolation, which is about making sure that one user's task can't access or interfere with another user's data or processes. The second is performance isolation, which is about making sure that even if tasks are sharing resources, one task doesn't degrade the performance of another in an unacceptable way. These two goals are related, but they're not quite the same. You can have strong security isolation, but still have performance issues if resources are being contended, so Borg has to address both of these at the same time. What's interesting is that Borg doesn't try to achieve perfect isolation. Instead, it makes deliberate trade-offs to balance isolation with efficiency, since enforcing strict isolation everywhere would come at a significant cost in terms of resource utilization. For security isolation, Borg takes a relatively lightweight approach compared to some other systems. Instead of using full virtual machines for every task, it relies primarily on operating system level mechanisms. In particular, Borg uses features like Linux to-root environments to restrict what each task can see and access. A to-root essentially limits a process to a specific portion of the file system, so from the task's perspective, it looks like it's operating in its own isolated environment, even though it's actually sharing the same underlying system. In addition to file system isolation, Borg also controls how tasks are launched and what permissions they have. Users don't get direct access to the machines themselves. Instead, they submit jobs to Borg, and Borg is responsible for executing them in a controlled way. This helps prevent users from interfering with each other or with the system as a whole. It's important to recognize that this is not the same level of isolation that you would get from full virtualization or containers. These approaches provide stronger guarantees by more completely separating environments. Borg's approach is intentionally lighter weight. The reason for that comes down to trade-offs. Stronger isolation mechanisms introduce additional overhead, both in terms of performance and resource usage. Since Borg is designed to run at massive scale, even small inefficiencies can add up quickly. Another key factor is that Borg operates in a relatively trusted environment since it's used internally at Google. That means it doesn't have to defend against completely untrusted users in the same way a public cloud platform would. Borg's security model is designed to be efficient and practical rather than maximally strict. It provides enough isolation to safely run many workloads on the same machines while still maintaining high performance and utilization. Now, performance isolation is a more subtle problem than security isolation, because even if tasks are prevented from directly interfering with each other, they're still sharing the same underlying hardware resources. In a Borg cluster, multiple tasks can be running on the same machine at the same time, all competing for CPU time, memory, disk I/O, and network bandwidth, as I said earlier. Even if each task is behaving correctly, this shared environment can still lead to performance degradation. For example, if one task suddenly starts using a large amount of CPU or disk bandwidth, it can slow down other tasks on the same machine. This is especially problematic for latency-sensitive systems or services, where even small delays can have a noticeable impact. To address this, Borg uses a combination of resource reservations and resource limits. A reservation guarantees that a task will receive at least a certain amount of resource, like CPU or memory. This helps ensure that critical services have the resources they need to function properly. On the other hand, limits are used to cap how much a task can use, preventing any single task from consuming an excessive amount of resources and starving others. However, even with reservations and limits in place, performance isolation isn't perfect. Some resources, like CPU caches, memory bandwidth, and disk I/O, are inherently shared in ways that are difficult to fully partition. As a result, tasks can still interfere with each other. What this all means is that performance isolation in a shared system is inherently imperfect. Borg mitigates the problem using reservations and limits, but it accepts that some level of resource contention is unavoidable. For CPU resources, Borg relies heavily on the underlying Linux scheduler, specifically the Completely Fair Scheduler, or CFS, rather than implementing its own custom scheduler from scratch. The idea behind CFS is that it tries to divide CPU time fairly among all running processes, but Borg builds on top of that by influencing how tasks are prioritized. One important distinction Borg makes is that latency-sensitive tasks and batch jobs are treated differently. Latency-sensitive tasks are typically long-running services, like user-facing applications, where responsiveness is important. Batch jobs, on the other hand, are more flexible. They can run in the background and don't require immediate results. Borg gives higher priority to latency-sensitive tasks to ensure that they remain responsive, while batch jobs are allowed to use whatever CPU resources are left over. This creates a kind of hierarchy where critical services are protected and less critical work fills in the gaps. Another important behavior is that Borg allows tasks to use more CPU than they were originally allocated if and only if there is idle capacity available. So if a machine isn't fully utilized, tasks can temporarily exceed their reservations and take advantage of unused resources. This is called overcommitment, and it's a major reason why Borg achieves such high overall utilization. Instead of leaving resources idle, it actively tries to keep them busy. However, this also introduces some variability. Because tasks can exceed their allocations when resources are available and then be throttled back when demand increases, performance can fluctuate. That means tasks don't always get a strictly consistent amount of CPU access over time. Taking all of this together, Borg makes a very deliberate set of trade-offs when it comes to isolation. On one end of the spectrum, you could design a system with very strong isolation guarantees, using full virtual machines or other heavyweight mechanisms to ensure that tasks are completely separated from each other. This would improve both security and performance predictability, but it would also introduce significant overhead and reduce overall efficiency. On the other hand, you have a system like Borg, which uses relatively lightweight isolation mechanisms and relies on the operating systems and scheduling policies to manage resource sharing. This allows Borg to achieve very high utilization since it can pack many tasks onto the same machines and take advantage of idle resources through things like overcommitment. The trade-off is that the isolation isn't perfect, of course. Tasks can still interfere with each other and performance can vary depending on system load. Another important point to note is that this design works in part because of the environment in which Borg was designed to be run. Since it was used internally at Google, there's a higher level of trust between users and workloads are generally well behaved. In a less trusted environment, you might want or need stronger isolation mechanisms. Now let's talk about lessons learned. Which design decisions turned out to be important, which weren't, what challenges came up from practice, and what insights were actually gained from operating the system day to day. These lessons are especially valuable because many of them come from real-world constraints, not just theoretical considerations. At the scale that Borg is meant to run, small design choices could have a huge impact, and issues that might seem minor in smaller systems could become significant. One of the big ones highlighted in the paper is the importance of using declarative job specifications. In a declarative model, users don't tell the system exactly how to execute a job step by step. Instead, they describe what they want. Things like how many resources the job needs, any constraints on where it should run, and how it should behave. From there, Borg takes responsibility for figuring out how to actually run the job. It decides where to place it, how to allocate resources, and how to handle failures or restarts. This is in contrast to a more procedural approach where the user would have to explicitly manage those details themselves. By keeping the interface declarative, Borg simplifies the process for users and reduces the chance of errors. Another benefit is that it allows the system to make better global decisions. Since Borg has a complete view of the cluster and all running jobs, it can optimize placement and resource usage in ways that individual users wouldn't be able to do on their own. It also makes automation much easier. Because the desired state is clearly defined, Borg can continuously work to maintain that state, for example by restarting failed tasks or reallocating resources as needed. In essence, the broad idea here is that declarative configuration shifts complexity away from the user and into the system, which is especially important in large-scale environments where manual management would become very quickly impractical. Another major lesson from Borg is the importance of fine-grained resource management and overall efficiency. In Borg, tasks don't just request vague amounts of resources, they specify relatively precise requirements for things like CPU and memory. This allows the system to pack tasks onto machines more efficiently, reducing wasted resources. One of the main techniques Borg uses is, as I talked about earlier, overcommitment. The idea is that not all tasks use their full allocated resources all the time. For example, a task might request a certain amount of CPU, but only use a fraction of it most of the time. Borg takes advantage of this by allowing more work to be scheduled than the total guaranteed resources would normally allow, under the assumption that usage will fluctuate. Kind of like how airlines overbook flights. This helps keep machines busy and significantly improves overall utilization. This ties directly back to the isolation trade-offs we discussed earlier. Because Borg uses relatively lightweight isolation, it has the flexibility to overcommit resources and dynamically share them between tasks. If it enforced very strict isolation, this kind of optimization will be much harder to achieve. Of course, this approach isn't without risk, as I mentioned earlier. If too many tasks try to use their full resources at the same time, there will be contention and performance can degrade. But in practice, Borg generally manages this well enough to make the trade-off worthwhile. Scheduling can become very complex at a large scale. At a basic level, scheduling might seem straightforward. You have tasks that need to run, and you assign them to machines with available resources. But in a system like Borg, it's much more complicated than that. The scheduler has to consider a wide range of factors all at the same time. These include resource requirements of each task, such as CPU and memory, as well as constraints like hardware compatibility, data locality, and whether certain tasks need to run together or be kept apart. On top of that, there are different priorities to manage. For example, production services that are user-facing need to be prioritized over batch jobs, which are, as I mentioned before, much more flexible and can tolerate delays. Another challenge is resource fragmentation. Even if there are enough total resources available in the cluster, they might be spread across machines in a way that makes it very difficult to place a task that requires a specific combination of those resources. Because of all these factors, scheduling becomes an ongoing optimization problem rather than a one-time decision. The system has to continuously evaluate the state of the cluster and make adjustments as workloads change, tasks complete, or new tasks are submitted. Another major point is that failures are not rare events at the scale of Borg. They're expected, and they happen very regularly. In a cluster as large as Borg's, machines are constantly going down due to hardware issues, network problems, or maintenance. So instead of trying to prevent failures entirely, Borg is designed with the assumption that failures will happen. The system continuously monitors the health of machines and tasks. If a task stops running or a machine becomes available, Borg automatically reschedules that work onto another machine. This shifts the responsibility away from the user. Instead of having to manually restart jobs or handle failures themselves, users can rely on the system to maintain the desired state of their workloads. Challenges, of course, come with operating at a large scale like Borg does. One interesting aspect, as discussed earlier, is that Borg uses a centralized controller called the Borg Master to manage the entire cluster. Even though the system is distributed in terms of the machines running tasks, control is largely centralized. At first glance, that might seem like a limitation, since centralized systems can become bottlenecks, but in practice, Borg is actually able to scale this design quite far. A single Borg Master can manage a very large number of machines and tasks. That said, scaling introduces new kinds of complexity. As the cluster grows, the scheduler has to make decisions across a much larger pool of resources, which of course increases the difficulty of placing tasks efficiently. There's also more state to manage, more machines, more tasks, and more frequent changes. This makes the system very sensitive to things like scheduling delays or temporary inconsistencies. So, while the centralized approach works surprisingly well at large scale, it still requires careful engineering to avoid becoming a bottleneck. To wrap things up, Borg is a good example of how a large-scale system should be designed and operated in the real world. One of the most consistent themes throughout Borg is that it doesn't aim for perfect guarantees. Instead, it balances competing goals like efficiency, scalability, and isolation in a way that works well in practice. I mentioned this earlier regarding isolation, where Borg uses lightweight mechanisms instead of strict separation, and again with resource management, where it relies on the overcommitment to keep utilization high. Another important idea is that many of Borg's design choices are driven by operating at massive scale. Problems that might be minor in smaller systems, like scheduling complexity or resource fragmentation, become major challenges, and the system has to be designed with those realities in mind. Finally, building a system like Borg isn't just about getting the architecture right. It's about continuously adapting to real-world conditions, handling failures, and making trade-offs that keep the system efficient and reliable over time. Borg is a great example of how large distributed systems are shaped as much by practical constraints as they are by theoretical design.